Section 5.4a. So modeling real-world trig functions graphically. We're going to answer most of these questions graphically when necessary. And then the second part of 5.4 is an algebraic approach. So the first example, the depth d meters of water in a harbor, t hours after midnight, can be approximated by the function 12 plus 5 cos of 0.5 t, where time is greater than or equal to 0 but less than or equal to 24. So it says to determine the maximum and minimum values of the depth of the water. So if I were to just rewrite this equation, so it's kind of in the order that we like to see things, we have learned that the max and minimum values are going to come from our d value and our a value. So technically the max, so I don't have to even put this in my calculator at all, right? D is our central axis, so this is going to be our midpoint of the graph, and if our amplitude is 5, then our maximum is going to be the central axis plus the amplitude, which is 17 meters. And the minimum is going to be that central axis minus the amplitude, which is going to be 7 meters. Okay. The period of our function. Well, the period of the function comes directly from our b value. The cosine this is the cosine function, so the period would be
the next bassinet to the office, please. The next bassinet.
2 pi divided by 0.5. which gives us 4 pi. So in terms of the question, though, we don't necessarily want to keep this in terms of pi. We'd want to approximate this into time, which is approximately 12.57 hours. Okay, so the period of the function would be 12.57 hours. Write a suitable window which can be used to display the graph of the function. Okay, so if we think about graphing this in our calculators, setting up a windows, we know there's no such thing as negative time, so we're going to start this as at -2 just so I can see my y-axis. My x maximum represents to the time. It gave us the window at the start of the question, which was 0 to 24 hours, so we're going to kind of go along that basis and go to 24. Our y min represents the minimum and maximum depths, right? And so in this case, we still want to kind of be able to see where 0 is our x-axis, so we're going to leave this at -2. But we did figure out our y maximum, which was the largest depth of the water was 17, so I'm going to leave this at 20. Make sure your calculator is in radian mode, which it is, and then you can get a graph of your. Okay, so it looks like the graph is actually dipping below. And I just wrote this, graph this wrong. Okay, so it looks like right here is our sinusoidal wave. That looks a little bit better. Okay, so our x min would be at -2. Our x max we said was 24. This represents our time in terms of the question. And then our y min, we want to be -2 again. Our y max, we said was 20. This represents the depth. What is the depth of the water to the nearest tenth of a meter at 2 a.m.? So two ways you can do this is we could do this algebraically by substituting 2 into our time of our equation. So the depth at 2 would equal 12 plus 5 cos of 0.5 times 2. So on your calculator, right, we could go 12 plus 5 cos of 0.5 times 2, and we would get our answer of 14.7 meters. You could also do this graphically on your graph by going second trace, number 1 for value, typing in 2 hours, and getting that same value, 12.5. That does not seem right, so let's see what we did wrong here. Oh, my equation is still wrong. So let's try this one more time. Second trace, number 1 for value, 2, there we go, 14.7 meters. Okay. A ship which requires a minimum of 8.5 meters of water is in the harbor at midnight. By what time to the nearest minute must it leave to prevent grounding? So on our calculators, if I were to draw my 8.5 meter mark, right? If the ship does not leave at this time, then it's going to get grounded in the harbor. So it wants to leave at this point. So I'm going to go second trace, number 5 for intersect, to find that intersection point. And that gives me 4.692 approximately, my first value. And then you need to find the second. Oh, it just says by what time. Okay, so then we want to change this to hours and minutes. So 0.6924 times 60 minutes is approximately 4. So I'd have to round this down to 41 minutes, because if I rounded it up to 42, we've gone over the time, which is you're going to get grounded. Okay, so at 4:41 a.m. they must leave the seaport. And then what is the next time to the nearest minute that the ship can return? So we're going to go second trace to number 5 for intersect. We are now finding the second intersection point. This is the time when he can return, which is at 7.8740. Change that to minutes. Times 60 is, and then here, if I rounded this down to 52, then the time would still be not quite enough in order for the ship to return, so we have to round this up to 53 minutes. So at 7:53 a.m. he can return back into the harbor. So our rounding rules didn't really apply to this question. It was more in terms of context of the question, how to round the question. Here, 41 minutes, we actually rounded down to 41, and here at 52 minutes, we actually rounded up to 53. So we didn't even consider these decimal values. Well, we did, but we had to figure out in context of the question whether to round that value up or down. Okay, moving on to example number 2. It says a top secret satellite is launched into orbit from a remote island not on the equator. When the satellite reaches orbit, it follows a sinusoidal pattern that takes it north and south of the equator. The equator is used as the horizontal axis. So our horizontal axis here, or a central axis, is going to represent the equator. So we're going to have values above it and below it to represent north and south. 2 minutes after it is launched, it reaches the farthest point north of the equator. The distance north or south of the equator can be represented by the following function, where d of t is the distance of the satellite north or south of the equator, t minutes after being launched. Okay. How far north or south of the equator is the launch site? Answer to the nearest kilometer. So important information in this question, it says 12 minutes after it's launched, it reaches its farthest point north of the equator. So I'm going to put this in my calculator. Pi over 35 x minus 12. Okay, so now I'm going to think about my windows. Okay, t is in seconds, so time is in minutes. So when I think about my windows, right, we'll leave, let's go I don't know, let's try 60 minutes, see what that does. And then my y maximum, if we think about the equator, the horizontal axis, there is no d value here, so the x-axis is going to represent the horizontal axis or the central axis. And then the amplitude is 5,000, so the graph is going to go 5,000 above that axis and 5,000 below it. So my y minimum has to be at least 5,000. So I'm going to go to 5,500. And then same with my maximum. So my min and max have to be fairly big values. Again, you need to be in radian mode. Graph this function. Okay, so my estimate of 60 minutes was actually pretty good. Okay, so it says 12 minutes after it was launched, it reaches its farthest point north. So 12-minute mark about here. So this tells me anything above the x-axis is going to be north. Anything below the axis is going to be south. So this is an important information just to determine which side of the equator is north or south. So the question says, how far north or south of the equator is the launch site? So this is where the satellite is being launched. So this is obviously north of the equator. To find that y-intercept, we'd go second trace, number 1 for value, type in 0 for my x, and it's 2,369 kilometers north of the launch site of the equator. Is the satellite north or south of the equator after 20 minutes? What is the distance to the nearest kilometer? So I'm going to go second trace. Again, for value, I'm going to type in 20 minutes, and I get 3,765 kilometers. And at this point, it's still north of the equator. When to the nearest tenth of a minute will the satellite first be 25 kilometers south of the equator? Well, south of the equator would mean my y value would have to be a negative 2,500. Put that in for my y value. And when is it first at 2,500 south of the equator would be this point here. So second trace, we're finding an intersection point. Would be 35.33 minutes. To the nearest tenth of a minute, so 35.3 minutes would be my answer. Okay. All right, and then lastly, last question. In a certain town in Alberta, the time of sunrise for any day can be found using the following formula, where T is the time in hours after midnight and D is the number of day, the day number of the year. All right, so we're talking about sunrises. Okay, so again, write a suitable window which can be used to display the graph. Okay, so D represents the day number of the year. Well, if we talk about domain, a suitable domain, I would say, would be within a year's time, so 0 to 365 days. Where in this case, days would actually because we're talking about each day, day would have to belong to our whole numbers. Okay. A suitable range is talking about time is the hours after midnight, and a good range would be anywhere from sunrise, where T is a time and hours after midnight. So anywhere from midnight to when's the latest sunrise that we get in Alberta, I would say right around 9 o'clock or 10 o'clock. So 0 to 9 would be a suitable. And time in this case is going to be part of real numbers because we can have decimals and fractions, right? So in our equation, so again, I'm going to type this equation in my calculator, negative 1.79 sine of 2 pi x minus 78 divided by 365. Oh, I need to close that bracket first. Divided by 365, and then close all of that brackets, and then plus 6.3. So let's go to our windows. So we kind of figured out our windows already. I'm going to leave this at -2 just to see my y-axis, and I'm going to go to 365. So I'm going to just go to 400 just to see a full period. I'm going to change this back to -2. And we said this is going to go to like 9 in the morning. Okay, I know my graph was still on radian mode. All right, so there is our graph. This is going to represent our day number of the year, and this is going to represent the time after midnight in which our sunrise happens. Okay, so determine to the nearest minute when the sun rose on May 7th, which is the 127th day of the year. So on my graph, I'm going to go second trace, number 1 for value, and I'm going to type in 127th day. This was at 4.9629. So as a time would be 4 in the morning and approximately 58. So 4:58 a.m. So kind of almost middle of May, the sun rises at approximately 5 a.m. Determine on which days of the year the sun rose at 7 a.m. So here we're going to put in 7 a.m. for our time. We're going to find these points of intersection within the year, and then we got to figure out what day that is. So second trace, number 5 for intersect. Find this one over here first. Oops. So 54 point, so approximately the 55th day. And this would be day number 284. Okay, and that would be our final answer. If you wanted, you could convert this to the actual day of the year, assuming that day 1 is January 1. So there's 31 days in January. So if I take 55 minus 31, this would be on approximately February 26th. And then 284th day, well, January has 31 days. February has, if it's not a leap year, is 28. March is 31. April is 30. May is 31. June is 30. July is 31. August is 31. So we want to start adding all these values up, obviously. I'm at 212. So September has 30. October has 31. All right, so we're almost there. Okay, so we've gone through all of these months, so now we're into November. So this would be November. If I take 284, subtract 273, this would be November 11th, would be the 284th day. Okay, and that is modeling real world problems, all on our calculators.